This is an autonomous 6,000-ton freight train equipped with a 16-cylinder turbocharged diesel engine, a massive motor weighing 2.7 tons, and an adaptive steering system specially designed for rail tracks. Let's see how this giant operates. Today it is transporting 24,000 tons of iron ore to the port, equivalent to 685 semi-trailers. Such a huge load relies on this 5-meter-long giant engine, releasing kinetic energy of 4,500 horsepower. The braking system is paired with a powerful air compressor to control the 90-centimeter steel wheels. The two sets of 6-wheel automatic steering chassis make up a powerful tractor head to pull 24,000 tons. One is not enough, so in the middle of the train, there is a twin brother that works together, sharing the load. The brothers carry 24 wagons to the iron mine for loading, a fully automated process that loads 100 tons per wagon. The purpose of this is to maintain the overall balance of the train. Filling 24 wagons takes 3.5 hours. Once loading is completed, it's the train driver's turn. Now the train's weight has surged to 30,000 tons. The driver starts the train's diesel engine with 16 20-centimeter pistons running at high speed, outputting 4,500 horsepower. However, it doesn't directly drive the wheels. Instead, it functions to power a 7.5-ton large motor that generates 3 million watts of electricity. The electricity is distributed to 6 2.7-ton electric motors, each driving 2 wheels to move the train forward. The wagons are connected by a coupler, and unlike what you might imagine, the train doesn't start all wagons at once. Starting this way, even the strongest coupler couldn't withstand such tension. The coupler isn't tightly meshed, it can slide 15 centimeters back and forth when the wagons are still. This clever design allows the traction locomotive to initiate sliding by 15 centimeters to bring the second carriage forward, followed by the third, fourth, and so on. Only after the head is moved 300 meters does the last carriage start moving, which takes about 5 minutes. Once fully started, the train begins to accelerate. However, it starts to rain lightly, making the track slippery. Don't worry, we have a trick that's been used for nearly 100 years, spraying sand on the rails. A moderate amount of sand can increase the friction between the wheels and the rail, enhancing the train's safety. Human wisdom is truly boundless. Ahead lies Ross Bay, a necessary route for the train, featuring a 1.6-kilometer curve. We all know trains have no steering wheel, so how do they turn? The secret lies in the wheels. They aren't normal cylinders, but are tapered with no sharp edges, larger on the inside and smaller on the outside. When encountering a curve, the wheels will shift slightly sideways, enlarging the contact diameter of the outer wheel with the rail. As the wheel diameter decreases, the train can smoothly take a turn instead of derailing. Simply relying on the friction between the wheels and the tracks is insufficient for turning. Inside the train's head, there are 2 sets of steering assemblies for the road wheels. When the front wheels encounter a curve and begin to turn, they push the rear set of wheels to rotate in the opposite direction. This ingenious design is the secret to keeping the train on track. However, the train's journey forward is not without challenges, as dispatch received a warning. There is a problem with the track ahead, and an inspector is dispatched to investigate. This vehicle is quite special because it can travel on the rails, equipped with a set of devices similar to train wheels that allow it to navigate the tracks. The inspector quickly identifies the issue. A bolt on the track has come loose. While this doesn't impede the train's movement, it necessitates a reduction in speed. The inspector reports the situation to dispatch, which issues a yellow warning, requiring the train to reduce its speed to 16 kilometers per hour to ensure safe passage. After seeing the preliminary signal, the train accelerated to 60 meters and proceeded at a normal pace. At this point, the couplers between the train cars are in an expanded state, and the upcoming journey includes a stretch with some slopes. When the train goes downhill, the rear cars will accelerate due to gravity and may collide with the front cars, potentially damaging the couplers and causing the cars to detach. Therefore, when climbing, it's necessary to control the speed and close the couplers to ensure the train's safety. An experienced driver successfully navigated this stretch of slopes. This traction engine, costing $2 million, features a collision energy absorption zone, 2 meters long at the head, equipped to withstand 22 tons of impact from double-row steel columns, all wrapped in a thickened steel plate. The base is made of anti-collision steel with an oversized fuel tank capable of holding 22 tons of diesel. The strength of the cab and tank is very high, so the train has nothing to fear as long as the tracks are in good condition and it can reach its destination without obstacles. Let's take a look at the train's braking system. Behind the engine is a powerful 3-cylinder air compressor operating at 950 revolutions per minute, generating 620 kilopascals of high-pressure air stored in the cylinder. When the driver presses the brake, the compressed air enters the brake cylinder, pushing the piston, making the brake shoes clamp tightly against the wheel tread. Through friction, the wheels stop turning, and this 30,000-ton supertrain comes to a halt at the port. Today's mission is complete, and tomorrow it will face challenges boldly, continuing its journey.